All right, we're going to start section 4.2 now, which is a definition of vector space. You need to have your notes by you for this one or the notes from e-learning printed out next to you. In order for something to be a vector space, 10 different things have to be true. So we're going to be proving in this section if something is a vector space or if it's not a vector space. In order for something to be a vector space, all 10 things have to be true, which means we have to do a proof for every single thing. If it is not a vector space, then you just need to show one counterexample, one specific reason why it's not true. So in order for all 10 things to be true, it has to be true for every single vector in that vector space. So we need to use variables. So if you're going to prove something is true, you need to use variables u, v, and w, and so on for things that are in that vector space. If you are proving it is not true by showing a counterexample, then you need to use very specific numbers. So what I want to know is v. Let me make it a pen first. Is v which I'm going to say is the set of all ordered pairs of real numbers of vector space with standard addition and multiplication. All right, so this is going to be true, which means we need to show all 10 things are true. So I'm going to list them going down 1 through 10. So number 1 says u plus v is in capital V. So any two ordered pairs I pick, if I add them, they're going to be in that vector space. Well, if I add two ordered pairs, x, y, and ab, I'm going to get x plus a, comma, y plus b. Well, that's still in my vector space, so that's good. My second one. If I add any two ordered pairs, x plus y, a times b, it doesn't matter what order I add them in. I have to show this is true. I cannot just go, look, it happens. So what happens when I add them? I get x plus a first, y plus b second. Well, because of how the commutative property works with real numbers, I can say this is a plus x, comma, b plus y. From there, I can say it is ab plus xy, and we're good on that one. All right, number 3 is kind of the worst one I'm going to show. So number 3 says that the associative property works with 3 of my vectors. So if I do xy plus ab plus cd, but if I group the second 2, that's going to give me the same thing as if I were to group the first 2. So I need to show how this is going to work. All right, so this is going to be xy equals a plus c, comma, b plus d. Plus there. All right, so that's going to be x plus a plus c, comma, y plus b plus d, which I can break up to be x plus a, comma, y plus b, add to that the ordered pair c plus d, which is then x, comma, y plus a, comma, b, which I did first, so I'm going to put those in parentheses, then plus c, comma, d. So yes, I did show that that is true. Rules 4 and 5, or properties 4 and 5, are pretty quick and easy. 4 says there has to be a 0 vector such that when I add it, I get the original. So number 4 says if I take xy and add that to 0, 0, I'm going to get my original of xy, which is true. So that's good. Number 5 says there has to be an additive identity, meaning I'm going to add the opposite. So xy plus negative x, negative y is going to give me 0, 0. And that's good. All right, number 6. Now we go to our scalar multiplication. If I do c times xy, I get cx, comma, cy. Well, that's still a member of my ordered pairs, so I'm good there. 7 says c times xy plus ab. So I'm going to do a scalar times the addition of 2 vectors. And this says it doesn't matter if you do the addition or the scalar multiplication first. So I need to show this. All right. So this is going to be c times x plus a, comma, y plus b, which is going to be c times x plus a, comma, c times y plus b, which is really cx plus ca, comma, cy plus cb, which then would be cx comma cy plus ca comma cb, which is c times xy plus c times ab. So I did show starting off adding first is the same thing as I get by doing the distribution first. All right, 8 takes more time than I have to do, but you would start off by showing c plus d times a vector. You know what, I can do it. So let's do it. So let's do number 8. So 8 says c plus d times xy, but here I'm going to do my c plus d first. All right, so now I'm going to distribute that. So I'm going to get c plus d times x, comma, c plus d times y. All right, we'll distribute now. So I get cx plus dx, comma, cy plus dy. So that's going to become cx, comma, cy plus dx, comma, dy. Well, I can pull out a c times xy plus pull out a d xy. So yes, I can mathematically show that I can get either distribute the c and the d first, or distribute the c, then distribute the d, and you're going to get the same answer. All right, number 9 is the same thing, but with multiplication. So I'm going to try and save a little bit of time there. And number 10 says the multiplicative identity works. So 1 times xy equals xy, and that is what we do with scalars, so I know that is good. All right, so that one's all set. So as I said, here I just skipped 1 just for time reasons, but you need to show if something is true that all 10 of them are true, and you need to show it with variables. All right, so let's go over another one fairly quickly, which says, and I'm going to skip around for a minute here, is the set of all ordered pairs of real numbers, so kind of what we were doing before, numbers with standard addition, but I am going to define scalar multiplication. I'm going to define that to be c times xy equals cx, comma 0. So whenever I multiply by a scalar, that means I'm going to multiply the first term by the scalar, and the second term is going to become 0. So would this be a vector space? Do all 10 rules I went through hold for this? And the answer is going to be no. So you need to give me a very quick example of why this doesn't work. And one quick reason for why it doesn't work, giving very specific numerical answers, is rule number 10, scalar multiplication. Scalar multiplication says 1 times xy should give me xy. But according to this rule, when I multiply by 1, I get x, comma 0. That does not equal xy. So when I multiply by 1, I do not get the original. So therefore, it is not a vector space. All right, so I'm going to do a couple more problems on one more video.